Okay, welcome back everyone. So today is kind of an exciting day because we're going to be changing topics and talking about some more sophisticated methods, and they build directly on what we have been talking about until now. So we're going to use this motivating example, which is a synthetic data set here that is, there's two different kinds of labels, either class 0 or class 1. You can see some of them are blue, the others are green. And you can see that the green ones are mostly in the center and the blue ones are on the outside. And that means that there's going to be it's not a linearly separable data set. There's no way we can come up with a linear classifier that's going to do well in terms of classifying this data set. And so this is a problem that we faced also in the last unit. And in the last unit, we said, or we talked about using feature transformations as a way of somehow enhancing the linear separability. And that is one way to go, and that's what gave us the support vector machine with, for example, a radial basis function kernel. But the issue with that, and there's several issues, but one of them is that we never quite know if the kernel that we're using is really well suited to our data set or not. We're just forced to use one of these existing kernels, and it may not be optimal. We might not know also how to choose the kernel. So coming back, kernels are related to feature transformations. We called them phi, and we talked about how feature transformations can be used to enhance linear separability. And so in this unit, we're going to see if we can actually learn the feature transformation directly from the data itself, not just use one that was given to us like implicitly through the RBF kernel. So that's really the new idea, and that is the main idea that underlies neural networks and all of the amazing things that machine learning is doing today. So, I guess the second part of it is we're going to learn that feature transformation, and then based on those transformed features, we're just going to do linear classification, same as we've been talking about for the last few units. So let's be a little bit more specific in terms of how we're going to construct and learn that transformation phi. So this is just one way of doing it. There's other ways of doing it as well, but this is essentially maybe the most common way of doing it. And it works in two stages. So what's done in the first stage is we're going to learn, in this case, 4 transform features, and each one of them will be the soft output of a linear classifier. And then given those transform features, so these are like our phi of x, we're going to apply linear classification to give a final soft output. So let's be a little bit more specific. So over here on the right, I'm plotting 4 linear decision boundaries. Each one of them we can associate with a binary linear classifier, as we know. And so if we just take, for example, maybe this classifier, it's essentially trying to classify some labels into either being on this side of the boundary or being on this side of the boundary. And then we have another classifier that maybe is trying to classify some labels on this side versus this side, and so on. Each of these classifiers, as we know, will output a score, z, which is a real number. And as you go perpendicularly on one side of the boundary, z will increase. And if you go on the other side, z will decrease. So actually, we don't really know from this picture which direction is increase or decrease, but basically we know that as you move away from the boundary, z gets large, positive or negative, and when you're right on that boundary, z is exactly 0. Okay, and that happens for each one of these classifiers. There's some score z that corresponds to that boundary. And we also know that we can transform that score z to a number between 0 and 1, which we can interpret as a possibility, as a probability. And we can do that by putting z into this sigmoid, right? This is the sigmoid, and the sigmoid essentially looks like, this function. Something like that. And right in the middle, when z is 0, you get the value 1/2. And as z grows positive, the sigmoid converges to the value 1. And as z goes negative, it converges to the value 0. Okay, so given a real number, you can think of this as a mapping of the real line to the interval between 0 and 1, or from a linear score to a probability. And those probabilities are often called soft outputs. As we know with classification, if you want to make a hard output, you then quantize that probability to either 1 or 0. And then you just return one of those two integers. But sometimes there's more information. If you don't do that quantization, you can say, how close are you, how probable are you, how confident are you in the output? So these soft outputs give us a little bit more information than the hard output 0 and 1. Okay, so again, what we're saying is, in this two-stage approach to classification, the first stage is coming up with 4 different linear classifiers. Each one outputs a score, or equivalently, we can put that score through a sigmoid to get a number between 0 and 1, a soft output. And then in the second stage of classification, we use those soft outputs as the transform features, phi, and we put those into a standard linear classifier. That linear classifier is going to output a single soft output. We'll call it AO, O for output. And when we plot that output down here using this heat map where red corresponds to numbers close to 1 and white corresponds to numbers close to 0, you can see that it is returning values close to 1 for the middle of this, which is all of our green samples. And that's exactly what we want it to do, right? We want to classify green versus blue. And it's actually doing a great job. Okay, so this is just one way to do classification, you could say nonlinear classification, where we are learning the transformation that is used by that linear classifier. And the way we're learning it is we are learning the weights and biases of, in this case, 4 different linear classifiers. Okay. There's other ways to do it, but that is, it's sort of one of the most common ways of doing it. And that's why we're explaining it this way. Okay, so there's a lot going on here, a lot of important stuff. What questions do you have on this? Is this making sense, or is it kind of confusing? There should be lots of questions about this. Who's brave enough to ask some questions? Okay, I'll start at the back. First hand up.
I guess, how do you decide where to put the boundaries to begin with?
That's a great question. So what we're doing in this case is we're thinking of this second classifier as being logistic regression, which means that we're going to minimize binary cross-entropy loss. That is what's going to guide us. Binary cross-entropy loss on those final outputs. Those final outputs are a function of the weights and biases used in the second stage, but also all the weights and biases used for those first classifiers in the first stage. So basically, everything is being designed all together to minimize the cross-entropy loss at the end. That's a great question. Other questions? There were some other ones, yeah.
Would you combine all the lines and the gradients by multiplying them if there's a difference or
Well, so each one of these lines is responsible for essentially, you could say, computing one of our 4 transform features. So like if I'm talking about a sample over here, then I'm looking how far is that sample from the line, on what side of the line is it, and I'm essentially putting that number z through this sigmoid to get a number. And so for any given sample, I'm going to be computing 4 different transformed features, and then those 4 features I'm giving to a linear classifier that's going to have 4 weights and 1 bias. Does that answer your question?
Yeah.
Okay. All right, so what are some other questions? Okay, so why are we using 4 different lines here, 4 different features, transform features? Could we have gotten away with 2? What is this picture going to look like if we have 2 features? Any guesses?
We have to have an enclosed.
Exactly. We are basically trying to enclose this. So if we had only 2 boundaries, there'd be no way that we could distinguish between any of the samples here, green versus blue, right? So we need at least how many? 3. At least 3 for this to work. Could we use 5 or 10? Sure, right? We could just even get like more and more of a circular region. What's the disadvantage of using more and more?
Probably computation and overfitting.
Yeah, exactly. Computation is one issue. A second is, we have more parameters to learn. So given a finite data set size, we might face issues with overfitting, we decrease our bias a little bit, but we increase our variance a lot. Okay, so yeah, exactly. So 4 seems to work, decently well. Maybe it's not optimal. Maybe we could try with cross-validation different numbers of features here, but this works okay. Okay, so this idea that we are trying to enclose the green samples gives us a sense about the features we're constructing. In fact, like you can kind of, to a rough approximation, you can say for each one of these lines, it is bisecting the space into 2 halves, right? Like this half and this half. That's what that boundary is doing. So you could say maybe, to a rough approximation, I could think of, for this boundary, all the samples above being labeled with the soft output close to 0, and all the ones below with a soft output close to 1, right? Because that's essentially, as you start to get away from this line, your z's will get large, either positive or negative, and then when you put them through the sigma, those things will get close to 0 and 1. So to a rough approximation, you could say like this, gives us some sort of classification into maybe 0 and 1. And in fact, here are the pictures of the soft outputs using, again, a heat map. So dark red is 1, and then white is 0. And you can see for this boundary here, it's putting 0s above and essentially 1s below. And then for this boundary on the left, it's basically putting 1s to the left and 0s to the right. And so if you kind of think about all the boundaries doing this, 1, 0, 1, 0, it sort of tells you that when you're in this middle region, roughly speaking, the features that we've learned, phi of x, are going to look like, in this order, we're going to have, if we go this way, we're going to have 0, 0, 1, 0, roughly speaking. Does that make sense? Because this is like here, this would be 0, 0, 1, 0. So this second linear classifier is basically trying to look for that pattern. It says whenever we see this pattern of 0, 0, 1, 0, that corresponds to a green sample in this new feature space. Whereas all these other patterns, like 0, 0, 0, 0, or 0, 0, 0, 1, and so on, would correspond to the blue samples. So the job of that second stage is to sort of detect those patterns, which it finally associates just one of those intersection of half spaces, you could say, with the green samples. Okay, so that's the idea, kind of at a high level. If you understand this, then I think you understand a lot about how neural networks work. So any other questions about anything on this page? Okay, this contains the main ideas. Otherwise, we can just kind of look at it maybe with a bit more notation. So here's another way to view the block diagram of our system. So here we have the first stage and the second stage. The first stage, which we refer to as the hidden layer, is, again, it's a form of binary classification. So essentially, we know that in binary classification, that itself has two stages. In the first stage, we compute some linear scores, Z, using weights, feature, biases. And then we can put those real numbers through our logistic sigmoid to get numbers between 0 and 1. Those are the soft outputs. So here we're starting with our two features. We're putting it through this affine linear transformation where we can basically say like the first row of this weight matrix corresponds to the two weights that determine our first score. The second row corresponds to the second score, and so on. At the end of the day, we compute 4 scores, each is a real number. We put them individually through these sigmoids to get 4 numbers between 0 and 1. That is like the pattern that I was describing here, those 4 numbers. They're not going to be exactly zeros and ones, but when you look at the ones in the middle, they're going to be close to the 0, 0, 1, 0 pattern. Once we have those transform features, we called them phi of x in the last unit. The rest is just linear classification, as we learned back in Unit 5. So here we have a single weight vector, a single bias. We compute a single score, z0, that's a real number. We put that through a sigmoid if we want to make that into a probability between 0 and 1. And that's what we finally plotted over here. Plotted that number as a function of wherever you are in the feature space. So this is sort of what it looks like as a block diagram. So at a high level, you take your features, you do some linear processing, you do some element-wise nonlinear processing, and then some linear processing and some element-wise nonlinear processing, and you're done. Okay, so these kind of structures are called multi-layer perceptrons. In this case, there's 2 layers, the hidden layer and the output layer. In general, you could have more layers. You have many layers, and we'll talk about that in the next unit, but there's enough going on with 2 layers to describe a lot of concepts, and that's what we're going to focus on in this unit. Okay. And because we're using sigmoids for these nonlinearities here, there's a direct connection to logistic regression, and we can in fact think of this as just doing logistic regression, linear classification on these outputs here. So you can think of the first stage of this neural network as learning and providing the features, transform features, and the second stage, just simply doing linear classification on those features. This is also known as a 2-stage feed-forward neural network. Okay, what questions do you guys have on this? Okay, so what happens if I remove these nonlinearities? I just take them out. What happens to the whole structure? Are they important?
There is no transformation.
Yeah, maybe we can say it in another way. Will it work well if we take these out?
You have two linear transformation after each other, so the results are...
Exactly. If we take out this nonlinearity, then these two linear stages together are just another linear stage. And so basically we're all the way back to linear classification. We have linear, sigmoid, that's nothing more than linear classification. So the presence of these nonlinearities is essential. We need them to work. That's what's special here. By sticking these in, this is more than just linear processing, and we can build interesting features. Okay, but there's another kind of downfall to this. Because of these nonlinearities, it makes the optimization of these parameters more difficult. In fact, it makes the output here non-convex in these parameters, and so we're going to have to be more careful in how we learn those parameters. Okay, we'll talk about that in just a moment. Any other questions on this page? Okay. So let's talk about training the model. So we talked about this a little bit, but let's look at the equations. So all the things we have to train are these, the weights in the hidden layer, the biases in the hidden layer, the weights in the output layer, and the bias coefficient in the output layer. So let's just put them all together and refer to them as theta. That's what we have to train or learn. To do this, we're given some training data, like always, n, x, y pairs. These original x's are just two-dimensional in this example. The labels we assumed are 0 and 1. And because essentially we're using this model, so we're kind of saying that ZO, which is this number, the linear output of the last stage, because we're putting it through a sigmoid, essentially we're kind of implicitly saying we have this probability model, the probability that y equals 1, given the original features and given all our trained parameters, is just 1 over 1 plus e minus e0. This is just the sigmoid. But now what's interesting is that this score is computed from the original inputs using a pretty sophisticated transformation. Okay, this thing, it describes everything that happened from the input x to the output score. So all the way from here, all the way to here. And as we said, because we stuck in these nonlinearities, this is a lot more interesting than what we saw in the previous units where this whole thing was just linear. Now it's like there's linear, nonlinear, linear again to get the score. But still, you could say that the math is still basically the same. All that's really changed is this. This is no longer linear. This is now something more complicated. But still, we could use the same framework, maximum likelihood, to train our parameters. So we say that the theta, the maximum likelihood theta, are the theta that minimize the negative log likelihood, which we recognize as this. So this is just our likelihood model, y given x, theta. And we did the derivation of this back in unit 5 when the labels are 0 or 1, then we get this version of the binary cross entropy loss. So all of this is exactly the same as what we've seen before. Really what's different, the only thing that's different, is how that output z relates to our original features x. That has gotten more complicated. Okay. All right. And because, like I said, because of these nonlinearities, you can show that the output is no longer, or the loss is not convex in these parameters. It is convex in these, but not in these ones here. And so that's going to cause some issues for us. So we're going to get back to that later in the unit. So that's sort of at a high level how we train. more or less, we're going to use some sort of version of gradient descent here. We're just going to, maybe we'll have to tweak the algorithm a little bit. We'll talk about that. Okay, all right. Any questions on how we're training? Okay, so those are kind of the details. Now let's step back for a bit of context. So why are we calling this a neural network? Well, when you look at biological neurons, you have something like this, where there's a neuron. It has a bunch of things called dendrites. These things they're connected to other neurons, and there's some sort of charges that flow down these things called axons that connect them. And when those charges come in to this neuron, they sort of build up. This guy accumulates charges from the things coming into it. And after that charge reaches a threshold, this thing finally outputs its own charge down this way, and that flows to other neurons. So if you step back and you look at kind of maybe a simple mathematical version of a single neuron, this summation would be like the accumulation of charge in the soma. These would be these are they say X, like the X's in this model. The features would be like what's coming in from your other connected neurons. And maybe there's some weights. Maybe some of these, for whatever reason, are more sensitive than others. And then finally, this notion of the soma outputting only after the charge reaches a threshold is like a form of hysteresis. We can think of that as something like this. So charge, output. So once the charge reaches this threshold, then finally it outputs something. And in practice, this is probably not going to be perfectly square, so maybe it's something that's a little bit curved. And that's exactly what our logistic sigmoid looks like too, right? So really, the logistic, single layer of our network where you have some linear things and then, so this threshold is like the intercept coefficient. So here's our mathematical model down here. Right. So here's the inputs. We're doing some sort of summation, maybe scaling the inputs differently. And in some sense, comparing them to a threshold. And so when this is, significantly greater than minus this, then the output is positive, and our sigmoid produces something. Okay, so there's a direct link between what we're doing and what happens, roughly speaking, in these biological neurons. So that's why we think about this why it's given the name of an artificial neural network. All right, any questions on that? Okay, so a little bit of history. So these neuron sort of biological models were studied as far back as the 1940s. And already in the 50s, you had people thinking about artificial neural networks. At the time, they were thinking at first with things more like single layer networks. That's where the name perceptron was started. And basically, these single layer networks, as we know, are more or less like logistic regression. And in fact, back then, they were already doing some simple computer implementations of this. Back in those days, computers were pretty simple, vacuum tubes and all that. And we also know that logistic regression is also not very powerful. So altogether, even though they started doing stuff, they couldn't really do much sophisticated stuff. But in the 60s, people kind of built on those ideas, and one thing they developed is the backpropagation algorithm, which we'll learn about later in this unit. And it's essentially an efficient way to train the parameters when you have multi-layer neural networks. And that is sort of like, you could say, the first wave of artificial intelligence is back in the 60s when people were getting excited about all that stuff. And then there was a lot of hype, and then technology didn't really deliver. So then people sort of forgot about it for a little bit. But then in the 90s, there's another resurgence of the same ideas with more computational power. More people were looking at it. But again, a lot of hype, and not a lot was delivered. So then that was the second wave of AI, which then sort of died out. So that in the 2000s, if you were working on neural networks and stuff, you were thought to be a bit weird. Why are you doing this? We all know it doesn't really work, or it doesn't really do much. But there were people that still did work on this stuff, like Jeff Hinton and people that are very famous now. They still, worked on it, pushed things forward. And then in the around 2012, there was finally, again, with now much more computational power, much more data, many more network layers, there were some breakthroughs. First in speech processing and image processing, and then soon many, many other fields. And that's sort of where we are today, this third wave of AI. So hopefully, or I don't know, maybe it's a good thing if it dies out, we'll see. But so that's where we are. There is a lot of hype now. It's not clear whether the technology will deliver to the extent that the hype is there, but there certainly has been a lot of progress. It really has affected just about every field, scientific, engineering, business, health, society, everything. But it all kind of boils down to what happened, I guess, in the three waves, but especially what happened around 2012. And we're going to get into those details in the next unit. But for now, that's when we talk about deep networks. But for now, we're going to focus on these two-layer networks and try to understand them pretty thoroughly so that we can see what happens when we have more layers than two. Okay, so that's a bit of history. And so now let's just talk a little bit more generally about these two-layer neural networks. So more generally, we're going to have inputs that are going to be d-dimensional, not necessarily 2 like we talked about, but just some number d. As always, same number we've been using all semester, number of raw features. And the hidden layer is going to have essentially the same form as what we talked about. It's going to have, you're going to take those raw features, you're going to do some linear combinations of them, scaling them, shifting them, and you're going to put it through some nonlinearity. The nonlinearity is going to be called an activation function. That function is just going to be a scalar function. So it takes in a scalar, outputs a scalar. Sigmoid is one option, but it's not the only option. We'll talk about some others. But as we know, it's key that you have some sort of nonlinearity there, because if you take it away, then you're back to essentially like a one-layer system, not a two-layer neural network. Another thing we have to decide is how many hidden units to use. Like in the demo, we used 4, but that's another thing we'll have to decide. And then in the output layer, we're going to have, again, a kind of a similar processing architecture where we take the outputs of the hidden layer, we do some sort of affine linear transformation, so scaling and shifting. But now this output layer transformation might take a vector input and give you a vector output. So the hidden layer, scalar, but here, this one you can see in bold, generally speaking, vector in, vector out. The other thing about it that's interesting is that it's more or less optional for reasons that we're going to discuss. If you want to put it in there, it just affects how you describe the loss. If you want to take it out, you can do the same thing by defining your loss differently. In any case, the output itself is going to have a certain number of outputs. We'll call those DO. And so if we're doing binary, classification, typically going to have one output, which is just the class. But if I'm going to do classification, among like 10 things like MNIST, then I'm probably going to have 10 outputs here. And those outputs are going to be essentially my confidence that it's class 1 versus class 2 versus class 3. And I just want to pick the largest Z, for example. Again, these are multi-layer perceptrons. Okay, any questions on anything we said here? All right, so there is something that, to me, trained as an engineer, I was a little confused by the pictures that are often drawn by computer scientists. So with, in engineering, we learn about block diagrams that might look like, for example, like this, where essentially what we would call the systems or the transforms are blocks, and then the signals flow like as wires. Like maybe we don't need those, but you just have like some lines connecting. But it turns out that often computer scientists will draw the diagrams exactly the opposite. So in this picture, these circles represent the quantities themselves. So like maybe I have 3 input features, and then these are my hidden, like what we call AH outputs, maybe AO. And then all the processing that happens is actually represented along that line. So this is a very non-trivial line. Maybe a whole bunch of stuff is happening along that line to get there. So I just want to kind of point this out because it was confusing to me at first. But sometimes this is how they draw the pictures. Okay. All right, any questions? Okay, great. So, so coming back to this more general 2-layer network we talked about on the previous page, but again, using more of an engineering type block diagram, this is how it might look. So we have, in general, D different features. In the picture, there's 2. And then over here, we're going to use column DH, different transformed features. So H is going to be used for hidden layer. So D, raw features, DH. And then at the output, we might have DO, in this case 2. So here's our linear processing, our activations. They might be sigmoid, they might be something else, linear processing. And then here's the output activation, which I said is not going to be separable like this. It might take that as a vector, operate on that vector, and give an output. And these little pictures that I drew here actually correspond to the softmax function, which takes in this case, 2 inputs, gives you 2 outputs. And so here it's showing like if you plot versus, these are the 2 inputs, this would be one of the outputs as a function of the 2 inputs like that, and the other output as a function of the 2 inputs looks like this. So this would just be softmax, which is probably the most common activation here for classification when you have more than 2 labels, but it really could be other things as well. Okay, so again, hidden layer and output layer. Pretty similar form, except these activations are separable, whereas this one is not. And finally, as I mentioned before, we can think of that last activation as optional. So I'll discuss that in just a second. Any questions so far? All right, so let's talk about this hidden layer activation function. So these things here. Typically, you choose the same one to use in all those places. The one we've talked about so far is the sigmoid. So as we know, that has a function 1 over 1 plus e to the minus z. And it looks like this. And if you look closely, this is 1 as the maximum output and 0 as the minimum. And the transition here is when the input is 0, it's 1/2. Okay, so at a high level, we can notice that the output is bounded. Bounded above by 1, bounded below by 0. And it's not centered in the sense that the outputs are always positive. So, as your inputs vary, you're not going to get outputs that are 0. Your outputs are going to be somewhere between 0 and 1. Bounded, not centered. So another common alternative is the hyperbolic tangent. And the hyperbolic tangent ends up being exactly like the sigmoid in shape, except that rather than going from 0 to 1, it goes from -1 to 1. But otherwise, it's the same. So you could write it as 2 times the sigmoid minus 1. And so now you can see that when the input is 0, the output is also 0. So this is bounded and centered. And this often works a little bit better than the sigmoid. Maybe because when the data is centered, as you go from, maybe you have like 0 mean features, you put them through a network, maybe that gives you, also kind of 0 mean quantities, you put them through this, you get 0 mean. Maybe the data is somehow, that centered makes it a little bit more easier to optimize. So in principle, there should be no difference because you can always shift this with a bias on the next level, but in practice, you do find some differences when you make changes in these choices. There's a lot of complicated stuff going on with the loss and the optimization algorithm and the way that things are initialized. And so often it's not obvious what's happening, but you do notice differences as you make different design choices. Okay, so those two options are pretty popular in shallow networks that have, 2 layers, a few layers. But once you get to networks with a lot of layers, these things don't work well for reasons we'll discuss in the next unit. But what does work well is something called the rectified linear unit, which has this form. And when you look at it, it's basically 0 for all negative inputs. And then if the input is positive, it just repeats that input. So it's this function. And so at a high level, this is unbounded. It grows as the input grows. And it's also not centered. And there's variations of this where they've tried to make it more centered. They actually work a little bit better. But this is kind of the workhorse. It's very popular in deep networks, but it also works relatively well in shallow networks also. So this is just, these are 3 examples. There's many, many more, but these are probably the most common ones, at least for shallow 2-layer networks that people would talk about. Okay, the key is that they're all somehow nonlinear. All right, any questions? Okay. So those are the hidden layer activations. What about the output layer? Okay, so it really depends on the machine learning task that we're doing. So let's first think about binary classification. So as we know, when we do binary classification, we just need, at the very end, to have a single real number, score z, where when z is 0, that means we're absolutely uncertain about the class. When z is very large and positive, means we're quite certain that y is 1. And when z is very large and negative, it means we're quite certain that y is not 1. So it might be 0 or -1 or however we represent it, that alternative choice. So that's all we need is for binary, scalar z. And as we know, one thing we could do is we could take that scalar z and we could put it through a logistic sigmoid. And if we do that, what we get, we can interpret as a probability. That's essentially what our logistic model, it sort of converts this z to a probability. But we also know that that's not really essential. Like, if in fact all we do is output z from our network, that's fine because if I tell you z alone, and you just notice it's positive, you can say, well, my guess is going to be 1. And if it's negative, you can say my guess is going to be 0. You don't need to put it through a sigmoid to figure out how you should classify, right? And if you want to use cross-entropy loss to train, if you think about it, cross entropy loss was actually defined in terms of z. It was not defined in terms of this thing. So again, if you just want to train, it's enough to compute the z's and stick that into your loss function. So, but yet, in this example, in this unit, we actually did build our network by putting the z at the output through this sigmoid, and that allowed us to make that nice picture of the a's that were like either 1 or 0. But really, this is sort of optional, whether we want to do this or not. So we could either put it through a sigmoid or not. All right, so that's one option. Any questions on that? Okay, I'll show you the loss functions on the next page. Okay, so what about multi-class? So multi-class with more than 2 classes. So what we've always done is we've always outputted a list of scores according to the one versus rest idea. So the first score is like the score for being in class 1 or not. The second is being in class 2 or not. Finally, being in class K or not. We know that if we want to convert that to a probability mass function, a probability, a vector of probabilities that add up to 1 that tell us what is like the probability that was in class 1 and the probability in class 2 and so on, then we know we can put those scores through a softmax. And so this would give us that vector of probabilities. That's certainly something that might be useful for us to do. But that's just one option, because we also know that if we are just given this vector of scores alone, and I want to know, what's the most probable class, I can just look for the index of the largest z, and that's enough. I don't need to put it through the softmax. And if we want to use multinomial logistic regression to train it, that was actually, the way that we derived it, it was actually defined based on these z's alone. It was not defined based on the softmax outputs. We used the notion of softmax to construct the loss, but the loss was actually written in terms of the z's. So once again, we could build our network to just output zo, and that would be enough. So we have an option here, what we want to do. And then the final situation that we might encounter is when we're doing regression. So here we're not doing classification. We just want to, predict some real number targets. And maybe we have more than one of them. I think we've seen that in one of the labs where we were predicting several targets simultaneously. So in that case, if we want to predict k targets, we want our network to output k different numbers. And each one of these numbers we want to come as close as possible to the kth target. So in this case, we don't want to use any output activation function. And in fact, if we took those z's and we put it through something like a sigmoid, we might be really hurting ourselves, because a sigmoid is going to prevent the output from ever going beyond 0 and 1, and that means I just could never predict a target that was outside of 0 and 1. Right? So in regression, we just take like the linear output itself, and that is what we use for prediction. Okay, so this shows you kind of the flavor of why there's these different options, at least for classification. Regression, people just use the last stage linear output directly. Okay, any questions here? Okay. And finally, let's talk about the loss functions. Okay, so starting again with binary classification. As we know, for logistic regression, the way that we build our likelihood is based on this probability model. Probability that y equals 1 given x is a sigmoid. That sigmoid, as you can see, is written with the linear score here. So what we derived back in Unit 5 was the binary cross entropy loss, which we look at the negative log likelihood, and it took this form. We have a sum of our training samples, and we have this stuff here, And that was in the case that y was either 0 or 1. We had a slightly different version when y was 1 or minus 1. But as you can see, this loss is written directly in terms of the linear score. So if you put it through the sigmoid and you want to use this loss, you can't use the output of the sigmoid. You actually have to go back and use the input to the sigmoid. Now it turns out that there is a way to rewrite the loss based on the outputs of the sigmoid. We'll call them here AO. And when you rewrite the loss that way, it takes this form. And it has actually kind of a, I don't know, to me it looks a little bit more symmetric than this version. And so this is actually something that's close to what's called cross entropy in information theory. It has the form of cross entropy, and this is actually where the name comes from. So this was not obvious before why this thing is called cross entropy, but actually if you rewrite the loss in terms of the sigmoid outputs, then it has something that looks like cross entropy. Okay, so these are again two options. If you build your network to output the z's, and you train based on the network output, you better use this loss. But if you build your network to output the sigmoids, and you want to train based on the network output, you better use this loss. If you use the wrong loss for your model, it won't work, or certainly won't work well. So this is a pretty common thing students do, is they'll build their network one way, but then they'll use the other loss, and it just won't work well. Okay, so just keep that in mind. It's the same story for multi-class classification. The way we talked about the likelihood back in Unit 5, we talked about this softmax, and we talked about using that for the likelihood model, and we went through the derivation, and we found that it was possible to write the loss, known as a cross entropy loss, this way in terms of these linear scores z. Okay. Maybe over here I'll just highlight the fact that we're using A down here. So that is what we have been using, but it turns out that if you want to put those scores z through the softmax to get these PMF values, you can actually rewrite the loss function to use them directly. So here we have another essentially identical loss, it's just written in a different way. Okay, so these are your two options. Here you could use one or the other. You just have to make sure that the way you build your network is consistent with the loss you use to train it. Okay, and then finally for regression, the way that we derived the likelihood is we assumed that the noiseless targets were corrupted by additive white Gaussian noise, and that gave us this kind of Gaussian likelihood, and when you take the negative log likelihood, you get a quadratic L2 loss. And that was basically how we justified using L2, is it makes sense if your outputs are corrupted by additive white Gaussian noise. Now you will also find sometimes people like to, instead of assuming additive white Gaussian noise, they'll assume additive white Laplacian noise, which is a bit more heavy-tailed, which handles outliers better. In that case, this becomes Laplacian, and your loss, instead of having squares, it has absolute values. And so this is another popular option when training a neural network, is instead of using L2 loss, you use L1 loss. It works pretty well. So those are the two options. We can think about them both from the perspective of maximum likelihood under the assumptions we make about the noise. But probably the most common one is going to be this L2 loss. So yeah, so that's what I wanted to say today. Any questions about this last idea? Great, okay. So have a great weekend. We'll talk about training algorithms next time.